Okay, so we are going to, in this lesson, look at specific antiderivatives, specifically the antiderivatives of the trig functions and the exponential and logarithmic functions. So just in this whole scenario, please remember that an integral and a derivative are inverse functions of each other. Sorry about that. So when we talk about the antiderivative of cosine u du, its antiderivative is sine of u. So sine of u plus c. If we were to want to check this to see if it makes sense, think of this backwards. What's the derivative of sine of u? Well, the derivative of sine is cosine. So it makes sense that its antiderivative, or the antiderivative of cosine of u du would be sine of u. Okay, and then let's talk about sine of u. Its antiderivative is going to be the opposite of cosine of u. Now, why is this a negative or the opposite of cosine of u? Well, if you think about, ignore the negative for just a minute. What is the derivative of cosine of u? Well, the derivative of cosine of u is negative sine of u. So that must mean that the derivative of negative cosine of u would be positive sine of u. And then we have our other trig functions and their antiderivatives and so on. So in each of these cases, you'll notice that the derivative of tangent, for example, is secant squared. The derivative of secant is secant tangent, and so on. Now, the next ones I want to look at are the exponential functions. And so we know from, when we looked at the derivatives of trig functions and exponential functions, we know that e to the u du, we know that the derivative of e to the u is its own derivative. So e to the u, the antiderivative of e to the u du would equal e to the u plus c. All right, now let's take a look at what if we have something raised to the negative 1 power. Now, I didn't address this. We haven't addressed this before, and the reason why is because the antiderivative of u to the negative 1 is actually involving a natural logarithm. So let's talk about why you don't use the power rule for integrals. If you were to take u to the negative 1 and follow the power rule, you would say, okay, u to the negative 1 plus 1 divided by, well, your new power becomes 0, and you can't divide by 0. So that's why we have not addressed this until now, because the antiderivative of something or an expression raised to the negative 1 power, du involves the natural log of the absolute value of u plus c. Now I'm going to come back in just a minute and talk about why does this involve the absolute value. But let's talk quickly, or run through this one pretty quickly. If we want to say find the antiderivative of an expression that involves a number raised to a power involving a variable, then its antiderivative is going to be that particular function, a to the u, divided by the natural log of a. Okay, so those are your formulas for finding antiderivatives of trig functions and exponential and logarithmic trig functions. So, well, actually, these are just exponentials, not logarithmics. So I want us to go back and I want us to talk about why do we have the absolute value with this natural log. Well, first thing I want to do is I want you to remember that the relationship between y equals e to the x and y equals the natural log of x is that they are inverses. Okay, the graph of the natural log of, or not natural log, but y equals e to the x looks like this, and the graph of its inverse looks like this. And again, they're inverses because they are symmetric with respect to y equals x. Okay, but that's just extra. I want to talk about the relationship though, because they are inverses. If you remember that the x value of one function is the y value of the other. So the domain for this function is your x's is all real numbers, all reals. Let's talk about the range. The range for the exponential is your y values are all greater than 0. So that means that the domain for its inverse is going to be x is greater than, x has to be greater than 0, and the range will be all real numbers. Okay, and if you look at that, it's true. Your domain, your x's, are greater than 0, and your y's, your range, are all real numbers. So, if x has to be greater than 0 in our formula, we have to have the absolute value of x so that we force the values to be positive, okay? Especially when they're unknown. So we'll see that as we work through some of these examples. All right, so let's begin looking at some examples. And our first example looks like this. So we have the integral of 2 sine of x dx. And I want to find the antiderivative. Well, as a reminder, that 2 is a coefficient of sine. So we could write it this way. 2 times the antiderivative of sine of x dx. And that would equal, okay, you have your 2. What is the antiderivative of sine of x? Well, that would be negative cosine of x. This is an indefinite integral, so we need to add c. So, cleaning this up, the antiderivative of 2 times sine of x dx is going to be negative 2 cosine of x plus c. Okay? All right, and so I'm just using my formulas that are on the notes as I get used to these. Okay, so let's look at the next example. Our next example says to find the antiderivative of sine of x over cosine squared of x dx. Okay, so this particular example, we actually have to do some work on this because there is no antiderivative for this entire expression. You do not find the antiderivative of the numerator. You do not find the antiderivative of the denominator separately. But what you do or can do is you can rewrite this expression in an equivalent form. Okay, so this is where your properties and identities for trig functions are going to come in handy. Let's think first about this. I can take the sine of x over cosine squared x and rewrite it as the integral of sine of x over cosine of x times 1 over cosine of x dx. Because if I were to multiply those two together, that's what I would get. So I've not changed the value of the expression at all. Now, what do you remember about sine of x over cosine of x? That is tangent of x. So I have not changed the value of sine of x over cosine of x because tangent is defined as that. And let's talk about this 1 over cosine. What do we know about cosine? Well, cosine and secant are reciprocals. So 1 over cosine can be replaced with secant. So now I've gone from the integral of sine of x over cosine of x. Let me say that again. I've gone from sine of x over cosine squared x to tangent of x times secant of x dx. These two expressions are equivalent. They don't look the same, but they are equivalent. I've replaced sine and cosines in a way that we end up with an equivalent expression. Now, why did I do that? Because tangent of x times secant of x has an antiderivative. And that antiderivative is secant of x. That's the antiderivative of all of that. And then this is an indefinite integral, so I have to add c. Okay? So there's our first two examples. On our next example, we have, let's see what we have. The antiderivative of 4 sine of x plus 2 sine of x, 2 cosine of x, sorry about that, and dx, of course. And this is a great opportunity for me to remind you that, remember, this is the formula for area under this curve. So dx, remember, is your width. This represents the height. So let's go about finding the antiderivative. Well, first I think I want to do this just so that you remember and know that 4 is a coefficient of sine. So I can write this as 4 times sine of x dx, 4 times sine of x dx plus 2 times the integral of cosine of x dx. And now I can just find the antiderivatives individually, and I get 4 times the antiderivative of sine is the opposite of cosine, plus 2 times the antiderivative of cosine is sine. And so to clean that up, we would have negative 4 cosine of x plus 2 sine of x. Oh, and I cannot forget c. So this one didn't have anything I needed to like rearrange or rewrite. So now let's look at our next example. Our next one looks like this. I'm going to scoot this up a little bit. So I start out with the integral of 4. I like seeing the secant squared x plus cosecant x cotangent of x dx. And so this is what I want to find the antiderivative of. And because I have a sum of 2 terms, just like I had here, I think I'm going to rewrite this as this 4 times the integral of secant squared x dx plus the integral of cosecant x cotangent of x dx. Now, secant squared x has its own antiderivative, which is nice. That's tangent. So I'm going to bring down my 4, and I will multiply that by tangent of x, and then add cosecant times cotangent has an antiderivative. And that antiderivative is going to be negative cosecant of x. And then I will add c. So this will actually clean up to be 4 tangent of x minus cosecant of x plus c. All right, so this lesson is all about just getting familiar with and used to using the antiderivative formulas for sine cosine, tangent, just the trig functions and exponential and logarithmics. So here's what I'm going to do. I'm going to maybe skip over the next two examples, the next three examples. I'm going to let you kind of look through those. And, well, I didn't really, okay, I want to go to, let's move over to this one. Next to the bottom, let's look at this example. The integral of sine of 2x over cosine of x dx. Okay, well, sine of 2x, I hope you recognize that as a double angle. There's a double angle identity where sine of 2x is equal to 2 times sine of x times cosine of x. This is an identity, and I can replace sine of 2x with 2 sine x cosine of x over cosine of x dx. And so this expression right here can actually be cleaned up to look like this. My cosines are going to cancel, and I end up with the integral of 2 times sine of x dx. So believe it or not, this expression and this expression, these two expressions are equivalent. And now I can find the antiderivative of sine. I know my 2 is going to come down. The antiderivative of sine is negative cosine of x, and I'll add c. So this cleans up to be negative 2 cosine of x plus c. Okay? So there's this is the antiderivative of the indefinite integral. Okay, now looking at the next one. So our next example, I have the integral of x to the negative 1 dx. Okay, this is just, look at the exponent. This expression is raised to the negative 1 power. This has just a simple antiderivative, and that is the natural log of the absolute value of x plus c. And remember, this has to have the absolute value on there because x is an unknown, which means it could be positive or negative, and we have to force it to be a negative, or we have to force it to be positive. So there's your absolute value. Okay, your next example, pretty straightforward. I didn't really give a whole lot here. What's the antiderivative of e to the x dx? Simply e to the x plus c. And then the last example that we have is the integral of 5 raised to the x power. So now 5 is the base raised to the power of x. And if you look at our formula, we simply take the expression 5 to the x and divide it by the natural log of the base, which is 5. It's just a matter of using your formula. And then I will add c, and I'm done. All right, so that's finding antiderivatives of trig functions and the exponential functions. Okay?